Now let's take a detailed look inside what affects CPU performances. Like what are the different factors there? Of course, one is the clock frequency, right? If you go, you already kind of know or kind of intuitively know that if you go with a faster processor, like from 1 GHz processor to 2 GHz processor, you expect your system performance to be better. Like your program will be executed in smaller time, your response time will be smaller. Now, for a synchronous CPU, okay, the execution time E is related to the number of cycles, let's call it N, used by the program, and the clock period, which is T, which is implies like frequency is 1 by T, okay, which is related to, it's basically what this says is T is related to the frequency by the relation F equal to 1 by T. Okay, so we know all about the clock period. We have studied that in I think lecture 1 and lecture 2, clock subsystem. So we are talking about that clock period. Okay, so for a synchronous CPU, your execution time is basically how many clock cycle it needed to finish a program and multiplied with time period. So in this context, always remember we are talking about the CPU performance, right? That means number of cycle needed to complete user program code, not the system library code, right? User program code. And let's say there is n number of cycle is needed, you multiply it with T, that is your execution time. So that means it's n by F. F is the frequency. Now, if that is the relation between execution time and frequency and number of cycle, now there are two ways to improve your execution time, right? Either you decrease n in this equation, that is you decrease number of cycle, or increase frequency, right? Because frequency execution time is inversely proportional to the frequency. So these are two strategy is well adapted, and let's take again a problem approach. Like, okay, let's see if we have how we compare of the improvement. Okay, so here's the problem. A program runs in 10 seconds on computer A, and that has 4 GHz clock frequency. Okay, a new computer B is need to be built to run the same program in 6 seconds. So we have a target execution time. It used to be go in a 10 second. Now we need to finish in 6 seconds. That's the target being set from the market study and so on and so forth. So we need to improve our processor. Now it has been determined that the clock rate can be increased a lot. Like there is like unbounded increase, but it will need the program to run 1.2 times of number of cycle. Okay, so let's say your older system used to take n number of cycle. Now it will take 1.2 n number of cycle. But you can increase the frequency a lot, like but doing that you are also increasing the clock cycle for various reasons. There are various reasons they are kind of depending on each other. Now the fact given that it has to increase the number of cycle by 1.2 times. Now for this program, what will be the target clock frequency or target clock rate for computer B? So there are known elements, like we know the execution time in A and B, we know the relation between number of cycles, we know frequency of one computing system, only unknown is the frequency from other computing system. That's what we need to calculate. So we start with execution times definition, which is number of cycle by frequency for system A and system B, and then we take the ratio of system A and system B, which we know system A execution time is 10 seconds, system B time is 6 seconds, and NA by NB, that ratio is already given, it is 1 by 1.2, FB, and FA is, we already know, 40 gigahertz. So that becomes my equation to solve. And then with solving that, we can see FB is going to be 8 gigahertz. Okay. So 8 gigahertz is double of the 4 gigahertz. So we'll need to increase the clock frequency double from 4 gigahertz to 8 gigahertz. But you can see your performance is not doubled, right? It is 10 by 6, which is like about 1 point, like it's more than 1.5, but maybe 1.63 things like, but it is not 2. That's what I'm trying to say, that even if we can increase the frequency double, we won't be getting double performance improvement, because of the fact is always in a circuit, like from hardware perspective, if you are increasing the clock, you are somewhat compromising your number of cycle needed to complete the same program. So that's the reason that you cannot expect double performance improvement by just improving the clock frequency itself. It will go and decrease some other aspect of the computing system. Now let's go a little more deeper into this number of cycle definition. How do we compute it? Okay. Now there is this one metric called clock per instruction, or CPI. So clock per instruction is the average number of clock cycle required to complete an instruction. If you recall, like our sequential multiplier or sequential, I would say division especially, and sequential shifter, all of them completes its operation in variable amount of time depending on the what type of operands value we are giving it, right? There can be like different amount of time, especially let's think from a shifter perspective, like so we are shifting 5 bit versus shifting 28 bit needs 5 clock cycle versus 28 clock cycle. So it's kind of not a constant amount of time that little shift operation will take, right, at that point. So CPI is a measurement that tells us that on average how many number of clock cycle required to complete an instruction. So you can see that your instruction set architecture has like a bunch of instruction listed, right? Just look at CS147 DB for example. So if it had been a real life system that we built up, then we won't be able to avoid this kind of variable number of cycle needed for different type of instructions. Okay, so what we do first, what we say on average, how many cycles I need per instruction. Okay, let's think in a little bit different way with example with our project we are doing, right? So for our project, since it is very simple processor and we are using a combinational ALU, what we are essentially doing that one instruction like add R1, R2, R3 or BNE R1, R2 to L1, that kind of instruction, all of them takes 5 clock cycle, right? So because it needs to cycle through this 5 state: instruction fetch, instruction decode, execution, memory, and write back, right? So for us, for our system, the Da Vinci system that we are building up in project 2 and project 3, our CPI is constant and same for all the instruction, and CPI is 5. Like we need one instruction need 5 clock cycle to complete. So this is very uniform system for our case. So, and we can well determine from the underlying architecture that system has a CPI of 5. But real system and other complex system, not that every instruction will need the same amount of cycles. Okay, it can vary. It can take one instruction can take 5, another instruction can take 10, another instruction can 20. So we are kind of first target is to averaging out the all the instructions and say that okay, that is my CPI per instruction on average. So once we determine the CPI of the target processor, then we can formulate number of cycle in terms of number of instruction that program has, the target program we are executing, multiplied with CPI. So that's what the formula is. N equals I multiplied by CPI, where I is your number of instruction in your program, the program you are executing, and thus clock per CPI. Here we are taking the average CPI of all the instruction, because of course your program doesn't have only one instruction, right? It has multiple instruction. Also, in this at this point, I would like to point out that don't think that I is the, you just count, let's say you are given an assembly program, you just count the number of instruction from beginning to end and that's your I. That's not true. This I is number of instruction executed on that program execution. Remember, like, your program is not a flat program, right? It has decisions, it has loops. So depending on your input data and other various factor, what you are running, basically your number of instruction executed on the processor would vary, right? It really data dependent. So it in some, with some set of data, it can, let's say one loop can execute for 1000 time, and another set of data it can probably runs for 10 times, right? So that's how it will vary from data set to data set, that how many instruction is executed. So point is, I is not that number of instruction you are counting on your program from beginning to end. It is really the number of instruction is executed from beginning to end of the execution of the whole program. Okay, and means it can vary with the loops, it can vary with the decision making structure, and so on and so forth. So now, since we just introduced these two terms, I and CPI, so we can now compute execution time in terms of them, right? So remember, previously we said execution time E equals number of cycle by frequency. Replacing now number of cycle with I into CPI, then my execution time formula become I multiplied by CPI by frequency. Let's take an example. Computer A and computer B implement same instruction set architecture. Computer A has clock cycle of 250 picosecond and CPI of 2. So clock per instruction it takes 2 on average. And computer B has 500 picosecond cycle time with CPI of 1.2. So kind of their frequency is doubled in the computing B, we can say that. Now, which computer is faster and how much? So we are comparing performance A with performance B, which is by definition, it is execution time on B by execution time of A. And that means number of cycle for B multiplied by time period of B, division number of cycle needed in the A for the same program on, and time period on A. Now number of in B is basically I multiplied by CPI B and multiplied with TB, and then NA is I multiplied by CPI A. Like NB is I multiplied by CPI B, NA is I multiplied by CPI A. Both of them will execute the same number of instruction while executing this program, because it's the same program, same ISA instruction set architecture, so that amount will not vary. So Then we can just cancel out I and CPI B we know, CPI A we know, TBTA both are known. We are just replacing those variables with the real values, and we see we have a performance improvement of 1.2. But make sure that don't confuse that this is 1.2 is related to the CPI of 1.2. This is just an coincidence that it becomes 1.2 x faster. Okay. So our answer, computer A, is 1.2 times faster than computer B, even though computer B is is 2 times slower actually. So I think I mentioned that computer B has a higher frequency, which is not true, right? Because clock A has a cycle of 250 picosecond, means frequency is 1 by 250 picosecond, whereas computer A is 1 by 500 picosecond. Computer B's frequency is 1 by 500 picosecond, which is less frequent, which is less frequency, right? So computer B has slower clock in this case, in this example, and it is twice slower. Computer B is twice slower clock than computer A, but it has a little bit faster CPI, sorry, little bit less CPI as well. So we have a performance improvement of 1.2, not really 2x performance improvement between A and B. All right. Now, so far, what we have discussed in terms of CPI and number of instructions executed in the processor, we assumed that like those instructions are like almost similar, like our Da Vinci system, like which each instruction will take 5 cycles no matter what, right? Even some system, if they vary little bit each other, then probably on average it's okay, right? But in a real system, not that all the instruction will be executed in same number of cycle or similar number of cycle, like maybe like 5, 6, 7, that kind of thing. They can probably vary a lot depending on what type of instruction I'm executing in the system, right? And that's what I meant by the heterogeneous ISA, where instructions are not uniformly performed, right? Not uniformly performed in the same scale. Maybe one instruction can execute it in 5 cycle, another can take probably 30 cycle. That kind of instruction set architecture, if we are given and corresponding processor, then using average CPI would lead to much like erroneous comparison of the performance. Okay, it will be more error, like on average error will be much bigger than the real scenario in those heterogeneous instructions or architecture cases. So in that approach, what we ideally should do, we actually need to count CPI really per individual instruction. Okay, CPI per individual instruction, and then really count the number of each individual instruction executed during execution of a program, and multiply that with that CPI of that instruction, and then sum it up. We can take a little bit like I would say less accurate approach by maybe we classify couple of instructions as which are very similar in CPI. Let's say some set of instruction has CPI like 2, 4, 6, 8. Okay, we group them together in one group, and then another set has like 15, 17, 20, 21, and then we group them together. Another set of instruction, let's say, has like 50, 51, 55. of CPI, individual CPI. In that case, to ease up our performance calculation, what we can bucket them in each individual group. Like first group, okay, 4, 5, 6, let's say. So we can just make an average of CPI for that group. And then the second group we can make an average because they are kind of similar, not really the same CPI each instruction, but similar CPIs. And the other set has the similar CPI but higher number, so we average them out per set or per group of instruction. And then we apply this average CPI per group and sum it up. Okay, so in that case, our number of cycle is really like let's say there are n such groups, like I equal to 1 to n such group where we measure the average CPI of per individual group of instructions, and then what we say, we sum it over number of instruction executed per group multiplied by CPI, average CPI of that group. Okay, so most accurate would be we count individual instructions. Okay, number of individual instruction executed for the program multiplied with the CPI, clock per instruction, value of that instruction, and we sum it out for all the instruction relevant to that program. So this approach is less accurate but workable, and more accurate than taking a blind average API of all the instructions. Okay, so we group the instructions with the similar CPI and we group them in multiple groups, and each group we assign an average CPI for that group, and then we count number of cycle as an summation of instruction executed from each group multiplied by CPI of that group, and we sum it up. So that's the better approach for an heterogeneous instruction set architecture.